oli ne nuorten esityksetkin eilen. Siellä oli Italiasta ja en muista mistä se toinen nyt oli, mutta nekin oli hyviä. Yllättävän hyviä. Että oli oikein onnistunut. Ja sitten Good morning, hyvää huomenta in Finnish. Warm welcome to our LUMA Research Symposium. Today and tomorrow we have two excellent keynote speakers, Professor Jari Lavonen and Dr. Angela James. And this symposium has been organized together with Math and Science Education Research Association. Yesterday, we organized the Research Summer School, and our keynote speaker was Professor Markike from Germany, and it was a very excellent day. Thank you for it. LUMA Center Finland is a network of Finnish 11 universities and 13 LUMA centers. And we have a national task from Ministry of Education and Culture. Our philosophy is joy of science for all, and our logo tells about the future makers, and the light in the middle is the light in the students' eyes when they are engaged in science. And LUMA is shortly explaining luonnontieteet, natural sciences, and mathematics. And A means also all sciences. It's like STEAM. We have also LUMA Science Research Forum, and we have 4 different activities there. This symposium and summer school are one of those, and then we have a national research seminar every month during a school year. And then we have international LUMA research journal. And after this symposium, it's possible for you to submit a paper to our special journal number about this topic today. We trust on collaboration. We think that collaboration with all partners is very important for good and sustainable future. And of course, the research is in the heart at university network. Newest research in science, mathematics, technology, and they learning and teaching. And so today we are going to hear a lot of interesting research around the world. And our board has decided that we are trying to make together new solutions and actions, and we are using design-based research as our framework, but there are many kinds of research going on. We are promoting scientific literacy in many ways and doing research in this field, and all things that we are organizing, for example, Teachers Climate Change Forum this August, are our research and development projects. We have 16 different LUMA labs, tiedeluokka in Finnish, around Finland in different universities. We are co-designing new solutions together, for example, for sustainability. We have international LUMA news. You are welcome to follow it, and we have e-letter, so you can find out what is going in Finland. We just started our summer season, and our teachers have summer holidays just now. And after 2 weeks, we have midsummer, and these beautiful midsummer roses are everywhere in Finland, and a lot of joy around us. So shortly, I say only that together we are more and makers of future in our hearts. I hope that we all have fruitful days and also fun together. Networking is very important for good and better world. Thank you. Kiitos.
And welcome also from my part. I'm Veli-Matti Westerinen and the president of Finnish Mathematics and Science Education Research Association, which is one of the co-organizers, the other co-organizer of this event. The Finnish Mathematics and Science Education Research Association was established in 1983. So we've been operating now almost for 40 years. In 2 years' time, it's a time for sort of celebration. We arrange annual national research symposiums, as well as participate and collaborate with LUMA Science Research Forum in arranging monthly seminars, as well as summer schools, as well as this international symposium. And besides that, we keep in contact and collaborate with national as well as international research associations. So research association in science or in natural sciences, as well as in education. And we are in close collaboration, for example, with the Nordic research associations, as well as the European ones like ESERA or NORMA, so the Science Research Association, European Science Research Association, and Nordic Association for Mathematics Education. And if you're a Finnish and you're interested in science education research, you can join as a member. And if you are not Finnish, but you're interested in collaboration, you might be a chair or a member in your local research association, you can contact us, and you can find the contact information from our website there. So warmly welcome from my part and from the association part as well.
Okay, thank you, Veli-Matti. Thank you, your association, for great collaboration. So it's time to start our symposium. Warm welcome again. And next, it's my pleasure and honor to introduce our first keynote speaker, Professor Jari Lavonen. Jari Lavonen and we have known each other almost 30 years, and we have collaborated over 25 years. And I can say that as one teacher says that Jari Lavonen is our Einstein in the field of science education in Finland. He is very well known also internationally and making excellent work in science education. And here I collect some facts about Jari Lavonen. He has been researching science and teacher education for the last 36 years. Long career, lot of interesting research papers and publications. Also, Jari has written many books for schools and so on. But he has excellent roles, also Director of National Teacher Education Forum, and he is a chair of Finnish Matriculation Examination Board. And he has done excellent work such as PISA and TALIS advisory boards, and also working for national curriculum. So it's my pleasure, Jari, to warmly welcome you to be our keynote. The floor is yours. Thank you.
Thank you, Maija, for your very warm words. It was quite challenging for me to recognize myself based on your introduction, but so thank you very much. So it's my great honor to introduce one of our research projects to you. But of course, I would first like to say good morning, good afternoon, good evening, wherever you are. So it's my pleasure to share some outcomes of the Finnish science education research. And in this research project, there are other researchers. Janna Inkinen made her PhD thesis, and Kalle Juuti is my long-term collaborator like Maija. Katarina Salmelaaro is a psychologist and also participating in the project. And then we have the collaborators from the United States, Joseph Kratzik and Barbara Schneider. So this research is about this collaboration. So a short introduction and aims of the presentation. And then I would like to say something about the Finnish new science curriculum, what it emphasizes, and then introduce the teaching module developed together with teachers in so-called research practice partnership, and then some research outcomes, how the module designed together with teachers support students' engagement and achieving of the aims, and some discussion. So as I mentioned, this is a part of the international research collaboration, and the challenge, a kind of starting point in our project, was the lack of student interest in school science and science careers. Of course, there is variation among the countries how interesting students perceive science and careers, but Finland are among the countries where students have quite low interest in those fields. So how to increase engagement and interest in science studies and careers, that is the starting point. So the solution, as already mentioned, is a research practice partnership with teachers in order to design project-based learning teaching modules. So the project-based learning is the term we use for this pedagogy we have followed in this research. Of course, there are many interpretations of the project-based learning, and the origins of the project-based learning is in Dewey's work in United States in the early 1900s. But this is a specific orientation inside this umbrella, and I will introduce the idea. And the question I am aiming to answer in this presentation, so how these teaching modules designed together with teachers, how they support student engagement and students' learning. And the case is upper secondary physics in this case, but we have designed and made modules also for lower secondary level, and physics, chemistry, biology are the science fields we have designed those modules. So not going to the details about this challenge in Finland, but just two questions in the international PISA attitude questions. There are questions asked for 16-year-old students how much they enjoy acquiring new knowledge in science and how happy they are working on science topics. And the scale is here is the percentage of students who agree or strongly agree with the statements. It was a 4-point scale, so those students who tick 3 or 4, they are here. So the OECD average for this 2 question is around 60%. And as you see, Finland students are not so much enjoying or are happy with their working with science compared to OECD countries. And here are these United States and Chile, which are also our collaborators in this project. So the science curriculum, because when we are designing something with teachers, of course, the origin should be in curriculum. The curriculum is guiding the processes, and you should know something about the context. So what's new in curricula for lower and upper secondary school? So maybe this slide is more from the lower secondary, but it's quite close to what curriculum in upper secondary is emphasizing. So the curriculum emphasizes the attitudes and interests. So I already mentioned there is lack of those things in Finnish science education, and so that's why the curriculum is emphasizing. Second, the curriculum reduces the number of concepts. So it is emphasizing kind of disciplinary core ideas or disciplinary core concepts. And how we know which are disciplinary core ideas? They are important across science and engineering domains. They are used for explaining things, phenomena. They are generative. They are used for investigating and solving problems. They are relevant for personal, local, and global context, like energy or interaction or compounds and structure of atom. And these are the core ideas in science. And then the curriculum is very much emphasizing earlier we called them science process skills, but nowadays they are more often called scientific practices or scientific and engineering practices. The practices that are done by the scientist or engineering, asking questions or definition of the problem for solving, to solve in engineering sciences, and planning investigation, making investigation, analyzing the data, modeling, they are the practices. And students' active role in learning is emphasized. Students should be in the center in the learning, and collaboration. So this is emphasized in the curriculum. But in addition to these very science-oriented aims, our curricula in lower and upper secondary level is emphasizing transversal competencies. They are more generic competencies, and digi competencies, use of digital tools, is part of those. I already mentioned examples of the scientific and engineering practices, and this is just a list of those practices mentioned in our curriculum. The transversal competencies are discussed in European Union, here in Europe. It's discussed and in OECD. UNESCO is interested about learning of transversal competencies. One of the new kind of model or definition for transversal competencies is in the OECD Learning Compass and papers under that idea. And one way to describe those competencies quite well working with the science is to divide the competencies in 3 areas. First, the basic competencies. Know what, so core ideas, and know how, inquiring, problem solving, use of digital tools. Creative and critical thinking skills and learning to learn skills, or use of metacognition. And the third area is the so-called socio-emotional learning, behavioral and social skills, how people trust themselves. We can support the development of self-confidence. Also, the willingness to engage is important. So this is an international frame, and our national description of transversal competencies is quite close. So know what the multiliteracy is, concepts, big ideas, ICT competencies important, inquiry orientation, problem-solving orientation. They are emphasized in Finnish description of transversal competency, and also those thinking skills and socio-emotional learning area. The use of digital tools or modern technology in learning is one key topic in this LUMA days. So I just show you how our curriculum emphasizes the use of digital tools and media in education. The curriculum says that students should be able to use digital tools in creative ways, collaborate and network, work with data, information, and knowledge. So these are general aims, and they should be integrated to all school subjects. And in order to achieve those aims, the curriculum also outlines how we can guide and what kind of processes we can guide students in order to learn those skills or competencies. It emphasizes critical and creative practices like search for information and generating of ideas. It emphasizes collaborative knowledge building and constructing and working with artifacts in and out of school learning environments. So this definition is actually quite close to the learning science research outcomes. If I have to put everything in the nutshell, I put one slide for what is the learning science emphasizing, and actually what is also emphasized in the curriculum. So the learning science emphasizes that we should engage students in learning through practices and maybe change practices, because the idea is that maybe we are more delivering information, and so students should be more active in learning. And also digital tools are important. And how to do that? So the first idea is the knowledge building approach. We should put students' ideas in the center. And second one is the knowledge practice approach. So we should follow in this case, scientific and engineering practices. If we are in teaching history or social science, of course, it's another type of practices. But in the case of science, the scientific and engineering practices, which are typical to real science. Social interaction and collaboration is important. So these four are important kind of preconditions for engaging students in learning according to learning science research. And the fourth one is working with artifacts. So in this context, we can understand that artifacts are very concrete, like Lego robot. It could be that kind of artifact, or it could be also the scientific model. Students are collecting data, analyzing it, working together, communicating the data, and making a model describe the phenomena they are investigating. Contextualizing is important in science education. We are taking examples from the real world, and we are giving examples how the scientists are working. This is how to contextualize. And of course, teacher's role is important. Asking questions, guiding what you have done until now, what you are planning next, what you know based on the phenomena, what is your evidence. So this kind of questioning and supporting is important in science learning. And then finally, the use of digital tools. So in a nutshell, what the learning science says, it's quite close what the curriculum emphasizes. An example from the primary level, students are working with the Arduino and making some concrete solutions. So they are collaborating, working around an artifact, putting their things and they are active in this work, what they are doing, and they are following the engineering knowledge practices. So this was background and the context of Finnish science education curriculum. Let's have a look for the module we developed together with teachers. I'm not able to give examples of many modules, but I give an example of one module we developed. But before I introduce the module, I make some definitions for how we understand engagement, interest in this context. So a lot is already known about engagement and interest in learning. This is an old idea that the content have an influence to development of the interest. Also the context. If we are teaching science in kind of science context without any additional context, it might be boring. But if we take for example, the environmental context, it is much more interesting for students. There is evidence for that. Relevance. What is the relevance for studies, personal values? What is the relevance for further studies? And activity. For example, in collaboration, students might be more interested. So I was thinking that we can build up a Padlet during my presentation so you can make notes. And in the end of the presentation, we can take a look what you have collected. So the Padlet is a tool in internet. You can generate ideas. And I have put those 4 main reasons for supporting the development of interest. And you can add ideas. You just click the plus and then you can add an idea what kind of content might be interesting and what kind of context might be interesting and so on. So in the chat, there is a link to this Padlet, but you can also make this ERQ code. You can make the link through that. But there is a link in the box. And we come back to this Padlet in the end of the presentation. So we all know that it's, for example, science inquiry has often said that it is really engaging for students. And we have an idea that the science collaboration is engaging for students. But the research is actually not so much supporting these 2 claims. The Potvin and Hasni made a kind of review, systematic review of 228 articles related to interest, motivation, attitude, engagements towards school science. So among those articles, they selected through a certain procedure. They find only 8 articles which really have kind of serious research, good design, and big sample, and that kind of things. 8 articles about how inquiry-based science learning influenced the students' interest. And only 2 articles reported improvement in interest. And in the same review, they find 9 articles about the influence of collaborative or cooperative learning to the student interest in the context of science. And 8 of them reported improvement in interest. So it is actually quite challenging, even we know those ideas in practice, how to put the ideas to the practice is really challenging. So we recognized this challenge when we were engaging with teachers to planning the teaching modules. So we have used in our research the definition for engagement according to Csikszentmihalyi research on flow theory. And according to Csikszentmihalyi ideas, there are certain preconditions for engagement. The first one is situational interest. So what is the student interaction with the environment and how that supports the student interest? Content and context, for example, or activity. The second precondition is student skills. If you are not having enough skills, what you are learning, it's very challenging and you lose your interest. On the other hand, if it is too straightforward, the learning is not supporting the development of interest. There should be a certain level of challenge. But what is important is that this student skill and challenge are in a good relation. Enough challenge and enough skill, then you become engaged. And the third precondition is the interest. So this is our theory behind the engagement. These three preconditions, interest, skill, and challenge, are important for the development of engagement. And if I compare this model to more general models related to the engagement, I can easily recognize that in generally, when we are discussing about the engagement, we are discussing about emotional engagement, cognitive engagement, and behavioral engagement. So the emotional engagement is in this theory is in the interest field. And cognitive engagement is the relation between the challenge and skill. And of course, students are engaged in scientific practices. There is a lot of behavioral type of engagement available, hands-on type of engagement. So this is our definition. The project-based learning is also quite close to the learning science research outcomes. And I mentioned in the beginning, there are actually many definitions for project-based learning. We have followed the Bloomfeld, Kratzik, Cherniak ideas about the project-based learning. And according to definition of those researchers, it's important that teacher and student have a driving question in their mind while they are engaging in learning. I mean now a little bit longer period than one lesson, maybe 2 weeks. A driving question is guiding learning during 2 weeks. It is a little bit overall question that the students and teacher are aiming to find an answer. And then, according to this driving question, students are exploring the phenomena. They are active in building knowledge. They are themselves active in asking questions. Okay, they are the scientific practices they are doing. They are asking the questions and planning and collecting data, making models. It means that they are active in scientific and engineering practices. They are active in collaboration, and they are producing artifacts, which are external representation of the learning, like a table or graphical model or whatever they are building up. And teachers' role in scaffolding is important. And this example is about the kind of basic Newtonian mechanics in the first grade of upper secondary. It is quite close to what is done in lower secondary in Finland. So the aim for this teaching module is that students learn to analyze data on the motion and recognize the objects, how they move, especially when they move with constant or changing velocity. The curriculum in Finland emphasizes the use of knowledge, and that's why the aims are also described in that way, the use of knowledge in practices. So that's why the aims are described in a way that students are really doing something in order to make some conclusions based on what they are doing. And second, we analyze the relationship among the net force on macroscopic object, its mass and acceleration. And then the aim was to learn how to apply scientific and engineering practices. And the curriculum in Finland is really emphasizing those practices in science. So they are the objectives for the teaching module. These are short video clips from the classroom. And I emphasized in my definition to project-based learning that the driving question is important. And here you can see how the teacher is supporting students to recognize the driving question. he makes a demonstration.
Siten, että täällä on ekana
There's one coffee filter and
kortin papereita ja sitten täällä on laittu sisäkkäin, niitä on 2.
There are 2 coffee filters.
Ja voidaan
so
lähteä
the mass is higher
samalta korkeudelta
on the left hand side. So the heavy object comes first.
Voidaan havaita jotain.
They are shortly discussing what they observe. But this experiment continues, and next the teacher is taking the filters, 4 filters, 2 filters, and then 8 and 4. So increasing the number of filters, but having all the time double mass in the other. And when you have 8 filters and 4 filters, you are putting them falling. They are coming about the same time. So it is quite amazing phenomena if you are supporting students to recognize that it is amazing. So sometimes the objects comes at the same time and sometimes different time. So the driving question of this module is, why do some objects take different time to fall down? So this question is somehow covering the basics of the dynamics and basics of the kinematics. Those terms are not used so much here, but anyway, it is a very challenging phenomena to solve. And then teacher is continuing the introduction and little bit contextualizing. So the internet is full of video clips how can be used for contextualizing phenomena. And of course, they are discussing about the phenomena. After having this kind of introduction where you are coming to the driving question, you are also contextualizing learning to everyday phenomena. We come to the situation when students are starting to ask questions. And here the students are using the learning management system and they are writing down the possible questions that could be investigated in the area of this phenomena. And later on, they are classifying the phenomena. And after doing those questions, after making the classifications, it comes quite clear that it is important first to make research or investigation on the movement as such, and second, make the investigation on the reasons why the movement changed. Sometimes the movement happens with the same velocity and sometimes there is a changing velocity. But you can split the phenomena to the 2 areas. And here the students are doing research about the movement as such. What is the movement for falling
Se voi pitää, joku voi pitää tuolla ylhäällä ja sitten alapuolella. Saatte itse päättää, mitä mittaa. Tässä ei ole mitään väliä, miten mittaa.
I was not emphasizing in the beginning the use of digital tools, but I hope that you were able to recognize that students were using and teach also in a many way the digital tools. But what is characterizing the use of digital tools is that they are used within the scientific knowledge practices. The asking of question, it is supported by the learning management system. Students are writing down the questions. They are introducing the questions to each other. They are discussing about the questions. While they are making investigation, they are using the microcomputer labs and so on. So they are together with the practices. And then the students get some data. They are analyzing the data. Communication is important. Actually, in the project-based learning, there are many situations when students are communicating. They are communicating the research questions, analyzing the questions. They are communicating the first preliminary models and discussing about that. That is important. So this was an example of the project-based learning unit or module in Finnish science education. And then let's have a look how engaging that kind of working is. And the data is collected from that phenomena I introduced you in the example. So we had this kind of experiment group and control group, kind of quasi-experimentation. There were 3 classrooms in the experiment group and 2 classrooms in the control group. So, and this is one example of our research. There are many types of data collection situations, but this is one example. And we were measuring the student engagement in situations. So we used the mobile phones for asking students how they feel now, the interest, how they feel now, the challenge, how they feel now, the skills. The measuring in a situation is important because interest and engagement are situational phenomena. You can develop the interest, but you can also lose it. That's why it's important to make the measurements in situations. So there were altogether about 1,000 engagement measurements for both groups. But of course, these are small number of classes, and it's not possible to generalize the outcomes. It's more like a case study, even it is this kind of quasi-experiment case study. So I mentioned that we used the mobile phones for measuring the engagement. So the students had phones. We were preparing for data collection. There was a questionnaire that was coming randomly selected situations. And students were asking how you feel the challenge now, what you are doing, and what is your skills now in this situation, and how interesting is this activity you are doing. And of course, we were also asking what is the activity you are doing. And students have to tick, are they asking question or building a model or something else? So many measurements in situations. And this is an example from the classroom when students are answering the questionnaire in random situations. So the engagement, in average, it's not so often students are engaged in learning science. In a big data, we have more than almost 100,000 measurements. So in average, about 10% of the randomly selected situations, students are engaged in learning. The skill, challenge, and interest are high, all those 3. And you can see that there is variation between the classes. So even as teachers are having the same module, you can see that somehow some teachers are able to implement the module in a way that it's coming more engaging. On the other hand, of course, we should understand that it depends on the class. What are the characteristics of the students? But anyway, there are variations between the classes. And now let's have a look how engaging are the scientific practices. And again, you should remember that the average is around 10% of the random selected situations. And how are these? In the project-based learning class, asking questions and developing models are the most engaging. Also, they're making argument based on the data. So the scientific practices as such, they are more engaging than situations in average. And they are also more engaging in the project-based learning class than the traditional class. But for example, planning investigations and conducting investigations, they are more engaging now than in the project-based. But in the project-based learning, we emphasize this planning and developing of models and communication aspects. Okay, and now in my video clips, you saw that the digital tools were used within the practices. And we made also analysis how the digital tools, use of digital tools as such, how they engage students. And we were not able to recognize if we compare the situations in general when the digital tools are used to the other situations, there were no difference. So the digital tools as such are not making, based on our data, science learning more engaging. But if you are combining it to the scientific and engineering practices, then it's a kind of natural way of using them, and they are supporting the development of engagement. So the use of digital tools, we should always ask how it is supporting the collaboration, how it is supporting the knowledge practices. It's not the question how often, how much you are using digital tools. It's more about the quality, how you are using them. And what about learning? I think it's not enough that students are engaged. That's not enough. We all think that the learning activity should be supportive for learning outcomes. So we also use a questionnaire for measuring students' learning outcomes. The questionnaire was designed together with teachers. 14 items were measuring different type of knowledge, especially the conceptual knowledge, but also procedural knowledge. Some items were more focusing to the conceptual knowledge, and some items were more focusing to the procedural knowledge. They were measuring the practices, and 1/3 of them were multiple choice items. And while we were designing the questionnaire, there were many iterations, and we measured the reliability and other things. We used the RAS analysis for the items, how well they were working and measuring what we were aiming to measure. So also in this data collection, we follow this quasi-experimentation. This is an example of the question emphasizing the conceptual knowledge. So the person is playing football and kicking the ball, and after kicking, it is asked from the students that what are the forces acting on the ball. They will have those alternatives to choice. This was a kind of multiple choice questionnaire. And this question is more emphasizing the procedural knowledge or scientific practices. In Finland, we have snow, and it's quite common to go downhill with the sleds. Students were asked to pose questions which are possible to make research on. So the two questions, you are able to design an experiment. So this is very much focusing to the procedural knowledge. Of course, this is conceptual, is velocity and that kind of things are present. And then we made a kind of coding manual, classify the questions and write down what are the correct answers, and also the rules how to rate students' answers in the case they were not exactly correct. And 7 items were more focusing to the conceptual knowledge, and there was a pre-test and post-test, experiment group, control group. So the experiment group was a little bit better in conceptual knowledge. Both were achieving higher in the post-test, and both groups have progress. The difference between the post-test, pre-test, it was statistically different. But there was no statistical significant difference between the control group and expert group. So you are learning conceptual knowledge about the same way if you are using project-based learning or not. The procedural knowledge side, so there was a difference. So the experiment group was achieving higher than control group, or they made progress in this area. And only the experiment group, there was a statistically significant difference between the post-test and pre-test. So the project-based learning as such is not a simple solution for supporting learning, but in the case of procedural knowledge, it may be more supportive. But on the other hand, it is also supporting the learning of conceptual knowledge. Even you are using more time for planning and modeling than in a traditional classroom. But the big difference was in engagement. We should remember that. So project-based learning could engage students in learning, support students' science learning. Science teacher could support students to engage in making sense of the phenomena through changing practices. This simple picture, I think this is many messages. So if we are willing to engage students in learning through changing practices, we should think those 4 views: students' active role in learning, practices, social interaction, and artifacts. They are working with artifacts in the classroom. And digital tools, it's more question about the quality, how they are used, than how much they are used. So thank you for following my presentation, and now we can go to the questioning, and we can also take a look for the Padlet, what is there. I can see that you have added some nice ideas related to the content, context, but especially the activity. But you can continue the filling this, and you can share your ideas with other people following the presentation. But let's go now to the questions and comments.
Okay, hello, everybody. I have looked at the questions, and maybe I can just post them to Jari. The first question was, what about 6C skills?
Maybe but the science process skills, or what key skills?
I'm not sure what is meant by this, but 6C, does it sound familiar? Maybe something related to inquiry-based learning?
It's quite often the science process skills, like observation and what was the question about them? What are they?
Maybe they meant to ask, is it important, or should it be taken into consideration? Or
So earlier really teachers and science education researchers were more emphasizing those science process skills, but there is now a shift to the discussing about scientific practices. Maybe the idea is that inside the science lesson, there are different kind of scientific practices, like this asking questions, planning an investigation, collecting data and presenting the data, making evidence-based conclusion, building up a model. They are scientific practices. And the learning science research is emphasizing that you are not able to learn science without combining those practices to the learning. So they are together, learning the science concept and practices together. And that the project-based learning is very supportive for putting them together. I am not sure what was asked, but that is the answer to the question.
Okay, thank you. And then we had a question, how good are the science teachers in relating the engineering problem solving or engineering practices while teaching physics?
This was a quite new orientation in our curricula. It raised also those engineering practices. So the asking questions is a scientific and definition of the problem is engineering. Collecting data and making kind of evidence-based conclusions, that is a critical type of thinking. And in engineering, it is the more creative. So you are generating alternatives in order to solve the problem. So the both are emphasized in the curriculum. And actually in scientific type of working, while you are planning a research question in the school context, you need creativity, engineering type of thinking. And then you are planning an investigation, you are taking different kind of equipments, putting them together. It is also engineering type of thinking. So inside science, there are many situations where you are generating ideas and planning something, engineering type of thinking. But then you are critical, you are looking for your questions, how well they are done in the frame of earlier research. You are looking for evidence, you are making argument based on the evidence and combining the previous knowledge. It is also critical type of thinking. So in the scientific inquiry, scientific investigation, you have those both. But it is also in engineering type of working. You are having a problem, you are generating alternatives, you need a creative type of thinking. And then you have to evaluate the alternatives or ideas. You are using critical type of thinking. It's like a scientific thinking then. So both are in engineering and in science. And I think that's my understanding, that's why this engineering type of practices was coming to Finnish science education. In the OECD documents, they also emphasize that they are together, the scientific and engineering type of thinking. So I think it's a quite new orientation in general and in science education. Also in the United States, in science, the next generation science standards, it is emphasizing both the scientific practices and engineering practices, because both are needed in inquiry, both are needed in planning something.
Yeah. Okay, then there was also a question, how familiar are the teachers with engineering as a discipline and engineering practices?
In Finland, the physics, chemistry teachers are educated at the Faculty of Science. And maybe earlier they were mainly become familiar with the science topics, science practices, science inquiry. But nowadays, because the teacher education unit is located to chemistry department, physics department, I'm sure maybe Maija is better person to answer this. I'm sure that you are combining at the Faculty of Science also the engineering type of learning. You are making solutions. You are using scientific knowledge. That is also the curricula emphasize use of knowledge in different situations, use of knowledge in designing something. So maybe Maija could add something that how seriously now the chemistry teacher education unit is emphasizing the learning of engineering type of practices.
Yeah, hello everyone. It's true. All this creativity is very important future skill, and we try to do our best. But I think that we should do it more in future. But we are trying to build new experimental activities. We have used, for example, 3D printers and these kind of things in chemistry education. So, but I think we should do it more and also do research more in the field to understand those challenges also in the field. But thank you.
I think this was a very good question and put us to think. In our faculty, I'm coming from the Faculty of Educational Sciences, and in primary teacher education, this scientific and engineering type of working, they are quite close. And in our research project related to primary teacher education, we have been developing the so-called invention pedagogy. So combining invention pedagogy and science inquiry type of working. But this is not topic today, but maybe the next time. So how to combine in primary teacher education the inquiry type of working and design type of working through invention pedagogy.
Yeah, and somebody also commented that there are some teachers who are very engaged and the others are not, so the engineering field is very large. So that's also probably true. Then there was a question, I am most curious of how the teachers perceive the general difference between scientific practices and engineering practices. Can you answer to that?
Yeah. So in science inquiry, you need both. But of course, the kind of big difference is the question. In science, we are asking why. So we are looking for explanations. And the practices are supporting that aim. in engineering type of working, we are asking how to make a versatile solution. So the practices are supporting for that direction. So that is the difference, why and how.
Yeah, also there was a comment that you can use an engineering practice to explain and open up a science phenomena. Most of the time it depends on the class and how much other stuff you need to do.
Yeah, good comment.
Yeah. Another question, what did you or could you change and clarify in your methodology after these researches? Would you make some changes?
So sometimes we use this control group. Sometimes we are just collecting the data from the class where we are having this project-based learning. And we have used many type of design. So once we were aiming to use the so-called single case study, this means that the same group was kind of control group and experiment group. So the teacher was using traditional approaches and project-based learning approaches with the same group. And we were collecting this experience sampling methodology data about the engagement through the traditional teaching and through the project-based learning. So we can see the difference between the level of engagement. But there are so many, it's not so easy to argue how this design is working, because the teacher is a human being, and if he or she has recognized that this project-based learning and the practices inside it is supportive for students, of course he or she is using them also in the traditional class. And that's why in some measurements we have used this quasi-experimentation, that we have had the traditional class and the project-based class and collect the data from both and having the same test for both. But you are also able to follow those data series, how the level of engagement develop in different situations. And if you know exactly what students are doing, you have the students self-report, what I am doing now. But in addition, we think that it's important to have a observation of the class or video from the class in order to recognize what students are really doing and have that additional information also to the interpretation of the data. So many ways to use the experience sampling method and the different design and our publications, they are in science education, International Journal of Science Education, Research in Science Teaching. They are made by different design. So maybe we can send the publications and people can see more about the design of the research.
Yeah, okay, thank you. Another question. I wonder what you meant by 1,200 or 1,000 engagement measures in the methodology part. Could you explain it in more detail?
So that is a good question to make it more clear. So this project-based learning period, it is typically 7 hours in our case, and one lesson in Finland is 90 minutes. So it's about 6 hours period. And then we are typically collecting the experience sampling method 3 times in this 90 minutes. So in one lesson, one student is answering 3 times. So in 7 hours, they are answering 20 times. And if there are those 100 students, then you get 120 times. But this data is really complex because it is nested. So the same student is answering many times. This means that the observations or measurements are not independent, they are dependent. So one dimension is the one student, and one dimension is the one student is answering many times, this time dimension. And that's why in analysis of the data, you have to use multi-layer modeling which takes into account these two levels. So you get a lot of data. Students are answering many times, and then you are really able to go to the real situations, how they feel. But then the data analysis is quite complex because we have to take into account how the data depends because the same student answer. But this type of data collection is really interesting if we compare this kind of momentary data in situation to the survey data. For example, the gender difference in physics, it comes very small. In a survey, when students are asked afterwards how they feel something, they are influenced by their attitudes when they are maybe not able to recall the real situations. But when they are answering in real situations, they are maybe more honestly answering. So the gender difference are much smaller, actually almost zero in the real situation than afterwards. On the other hand, we made a comparative research with the Chilean and Finnish data, and we recognized that this kind of personal interest influence a lot to the situations. So, but important to remember that actually, for example, interest, there are two types of interest, the personal interest and situational interest. There are different type of interest. And this is the way how you can become familiar with the surveys are for personal more and ESM measurements are for situational interest.
Okay, yeah, we're almost run out of time, but then also it was asked about the support that maybe the teachers had to include the PBL in the classes and how long time they had. Had they some materials or training or planning or something?
So how we support teachers to become familiar with the project-based learning. So,
yes,
it takes time. We recently published a paper to the Journal of Science Teacher Education. We had 10 teachers who were implementing the same module in first year and the second year. So there were some preliminary training before the first implementation, and then a lot of analysis of the data and discussions and reflection with teachers. And then redesign of the module and implementing the same module in the second year. So it takes more than 1 year to become more familiar with the project-based learning in order to support students' engagement. And we can see the big difference between the first year data and second year data. Teachers learn better how to support, how to scaffold student learning processes in a way that it is also engaging students. It's not a quick process. And that's why we call our collaboration with teachers the research practice partnership, that we are at the same level. Actually, we don't know so much. Together with teachers, we know more. Like in the LUMA, together we are more. So that's, but it takes time, not quick process.
Yeah. So I think we don't have any more time for the questions. It was really interesting. Everybody had interesting questions. Do you want to comment on the Padlet once more, or?
Oh, now my pad is sleeping. So I just take a look that there were most of the, okay, I not takes the time to open. But anyway, in the beginning, I looked the Padlet and it looks that there were more nice examples for the activity, how we can make the activities more engaging for students. Not so much about the content, some about the context. And the relevance I didn't look because I have to make it smaller. But you can continue making the Padlet and share ideas. You can learn from each other continuously.
Yes, okay. Well, thank you, Professor Lavonen, for this really interesting and important keynote lecture. And now it's time to have our lunch break, and I will give you some instructions for the future. So now we'll shortly inform you how this platform works. Eli lyhyt info Liveta-alustasta. Nu berättar jag hur Liveta fungerar och vad ska vi göra idag. So as you saw, the program of the event can always be found from the top of the site. The event rooms are listed on the left. On the main stage, you can find a program that's open for all participants. Oral presentations of the LUMA Symposium are located in room LUMA Symposium. You can also find the right room by clicking the links in the program. And please notice that all presentations for the symposium are tomorrow. Today we have this keynote by Jari Lavonen, and in the afternoon there is a start tea gala in which you are welcome to join. Eli ohjelma löytyy aina sivuston yläpalkista. Vasemmasta palkista löytyy virtuaaliset tapahtumatilat. Kaikille yhteinen ohjelma löytyy Mainstage-linkistä. Ja muu päivän ohjelma on sitten siellä eri huoneessa sen Mainstage-linkin alla. Voit tarkistaa ohjelmasta, missä huoneessa mikäkin työpaja järjestetään. LUMA-dagarnas program hittar du högst upp på sidan. Till vänster finns en lista på evenemangets rum. Program som är öppen för alla deltagare kallas för Main Stage. Svenskspråkiga verkstäder kallas för skolresurs. Förhandlingsmedlan för deltagare i verkstädet samt muntliga presentationer krävs inte. Du kan delta direkt på verkstaden startar. The event chat is located on the right. In addition to the general chat, different rooms also have their own chat. These chats are activated when entering the room. Eli tapahtumalla on yleinen chatti ja huonekohtainen chatti. Chat-funktionen finns till höger. No prior registration is needed for the workshops or oral presentations. You can simply join the discussion when it begins. For the afternoon coffee break, we have set up coffee rooms in 3 languages. They are to be found from the breakout rooms. Ja suomeksi löytyy vasemmasta sivupalkista kahvihuone-linkki. På eftermiddagen kafferummen aktiva på 3 olika språk. So now let's go to lunch break, and after that we have workshops.